Hello and welcome to another video from the Introduction to Machine Learning lecture series. In this section, we will go through a simple machine learning application and create our first model. In the process, we will introduce some core concepts and terms. So let us first look at what supervised learning means. Machine learning algorithms that learn from input-output pairs are called supervised learning algorithms because the teacher provides supervision to the algorithms in the form of desired outputs for each example that they learn from. Example, predicting house prices. So let us now look at an example of supervised learning. Suppose you have a basket of fruits and what you do is you label each of the fruit as an apple, okay, or you annotate it, whatever you like to call, and we send that information to our model to learn from it. Okay, so once the learning is done, now if you take a fruit which has attributes of an apple, our model will successfully predict that fruit as an apple. So this is an example of supervised learning where we are telling the model what are, suppose you have your data and you are telling the model that what the output should look like. Okay, and then when you give something like when you take some data which is once the learning is done and you take some data, or for example in our case we take a fruit which is an apple or a fruit that has attributes of an apple. So the model after it is done learning, it will predict that fruit as an apple. So this is a case of supervised learning. Now let us take a look at unsupervised learning. Unsupervised learning, also known as unsupervised machine learning, uses machine learning algorithms to analyze and cluster unlabeled datasets. These algorithms discover different patterns or data groupings without the need for human intervention. Example of an unsupervised learning would be a case where a supermarket wants to increase its revenue. It decides to implement a machine learning algorithm on its sold products data. So let us now take an example of an unsupervised learning. Suppose you have another basket with mixed fruit. For example, we can see that we have apples and watermelons. So now if we feed this to our model, the model will somehow will get into that how the model like learns, or how the model is able to classify or cluster the data, but it is able to do so, and it will give us an output where we have two categories of fruits. One is apple and the other one is watermelon. So here in this case we do not have what the output looks like. Okay, so the machine learning learns itself and sees attributes that are similar for a particular category and other attributes which are similar for a different category, and it segregates it. So this is how this is an example of an unsupervised learning. Okay, so now let us look at the first application, which is classifying iris species. Let's assume that a hobby botanist is interested in distinguishing the species of some iris flowers that she has found. She has collected some measurements associated with each iris, the length and width of the petals and the length and width of the sepals, all measured in centimeters. She also has the measurements of some irises that have been previously identified by an expert botanist as belonging to the species Setosa, versicolor, and virginica. For these measurements, she can be certain of which species its iris belongs to. Let's assume that these are the only species our hobby botanist will encounter in the wild. Our goal is to build a machine learning model that can learn from the measurements of these irises whose species is known, so that we can predict the species for a new iris. Because we have measurements for which we know the correct species of iris, this is a supervised learning problem. In this problem, we want to predict one of several options, the species of iris. This is an example of a classification problem. The possible outputs, which are the different species of irises, are called classes. The desired output for a single data point, which is an iris, is the species of this flower. For a particular data point, the species it belongs to is called its label. Okay, so let us now open the Jupyter notebook and see what the data looks like. So I have opened this Jupyter notebook And at first what I'll do is I'll try to import all the libraries that I'll need. So I'll do pandas import as pd, then I'll import the numpy library, numpy as np. What else? I'll import the scikit-learn library, and I'll also import matplotlib. Then at last I'll also import the cbound library as SNS. Okay, so the next thing that we'll do is we'll just explore the data a little bit. So at first what I'll do is from sklearn dataset import, you can use the tab key for autocomplete, okay, in Jupyter Notebook. And from sklearn.dataset I want the load iris, okay, and then save it to variable name load iris where we invoke the dataset, right? So let us first look at what what we have, like what are the few things that we have in this dataset. This dataset is in the form of a dictionary of keys and values, okay, key value pairs, okay. So let us first look at the keys that we have. Iris dot keys, and as you can see that we have data, target, frame, target names, description, feature names, file name, and data module, okay. So at first let us look at the data. So it is iris dot data, and you can see that we have we have a total of 150 rows and 4 feature columns. So we have 5 point. This is the first row which has values 5.1, 3.5, 1.4, 0.2. The second row has 4.9, 3, okay, then 1.4 and 0.2, and like this, okay. So what these columns mean is given by the feature names key, which we can just print it out as iris dot feature names. And you can see that we have sepal length in centimeter, then sepal width in centimeter, petal length and petal width. So this 5.1 in the first row is corresponding to the sepal length, then 3.5 is corresponding to sepal width, then 1.4 is corresponding to petal width, petal length, sorry, and 0.2 is corresponding to petal width. So this is what this data is. And we also have something called as target and target names. So let us first look at the target. So I'll do an iris dot target, and you can see that we have zeros, ones and twos, right? So what this 0, 1 and 2 means is in do it iris dot target names, and you can see we have 3 names, Setosa, versicolor and virginica. So basically 0, the target 0, the target value 0 is corresponding to Setosa, the target value 1 is corresponding to versicolor, and target value 2 is corresponding to virginica. So these are the 3 iris species that we have. And yeah, so these are the values data, then these are the like the feature names or the column headers for this data. Then we also have this target variable having 0, 1 and 2, which is corresponding to this 3 iris species. And what else, we also can have a brief description about our data set. So for that what you can do is I can print iris dot capital D, and yeah, so you can see that this iris plans data set, we have number of instances, that is the number of rows is 150. So it says that we have 50 in each of the 3 classes, that is for Setosa we have 50, for versicolor we have 50, and for virginica we have another 50. So attribute information, sepal width, sepal length, sepal width, petal length, petal width. So these are the 4 these values that we have seen. And we have the 3 classes, which is iris, Setosa, versicolor and virginica. And these are some basic statistics about our data set. Okay, so now what we can do is we can transform this data and put it in a pandas data frame. So for that, what we will do is I'll name it data frame equals to pd dot data frame, and then I'll the data needs to be data dot target, and the columns or the column names of the data frame could be iris dot feature names. Okay, okay, so so now if I like try to print the first 5 rows of the pandas data frame, we can see that we have this sepal length, sepal width, petal length, and petal width. What we can do, one more thing that we need to do is I'll try to include the target column. Okay, so for that we'll write like this, and I want to, yeah, so I think this, so I created another column and stored the data using the iris dot target. So as you can see that if we try to print out the first 5 rows, we can see that we have a new target column which has like based on the iris species, it will have corresponding values of 0, 1 and 2, right? So here we have transformed the data, that dataset, that iris dataset that we have into a pandas data frame. So now how to measure the success? Okay, so we want to build a machine learning model from this data that can predict the species of iris for a new set of measurements. But before we can apply our model to new measurements, we need to know whether it actually works, that is, whether we should trust its predictions. Unfortunately, we cannot use the data we use to build a model to evaluate it. That is because our model can always simply remember the whole training set and will therefore always predict the correct label for any point in the training set. This remembering does not indicate to us whether our model will generalize well, which means whether it will also perform well on new data. To access the model's performance, we show it new data that it hasn't seen before, for which we have labels. This is usually done by splitting the label data we have collected. So we have 150 flower measurements into 2 parts. Okay, we split the data, label data, into 2 parts, and one part of the data is used to build our machine learning model and is called the training data or training set. The rest of the data will be used to assess how well the model works. This is called the test data, okay, or test set. Scikit-learn contains a function that shuffles the data and splits it for you. The train test split function is used for this purpose, and this function extracts 75% of the rows in the data as the training set together with the corresponding labels for this data. The remaining 25% of the data together with the remaining labels is declared as the test set. Deciding how much data you want to put into the training and the test set respectively is somewhat arbitrary, but using a test set containing 25% of the data is a good rule of thumb. In scikit-learn, data is usually denoted with a capital X, while labels are denoted by a lowercase y. This is inspired by the standard formulation fx equals to y in mathematics, where x is the input to a function and y is the output. Following more conventions from mathematics, we use capital X because the data is a two-dimensional array, a matrix. That is because you can see that we have sepal length, sepal width, petal width, and yeah. So this is basically our the features which are obviously two-dimensional. So therefore, we use capital X there, and we use a lowercase y because the target is a one-dimensional array, that is a vector. For example, we can see that the target has just 0, 1 and 2, which is in one dimension. Let us now call the train test split function on our data and assign the outputs. Okay, so what I'll do is I'll do as from sklearn dot model selection. I'll import train test plate, and now I'll write this, sorry, then I'll write the variables, like assign the variables, and so I'll do x train y x test, y train y test equals to, then I'll again call train test split, and then I'll do iris dot data for x train and x test, and I'll do iris dot target for the y train and y test. I also have a parameter called random state, and I'll set it to 0. So what this random state hyperparameter does is, in the train test plate function, the random state parameter controls the shuffling process. Okay, with random state equals to none, we get different train and test sets across different executions, and the shuffling process is out of control. So to avoid that, what we do is we assign random state to be equal to 0, so that we get the same train and test sets across different executions, right? So now if I try to look at the data sets, okay, for example, if I look at the x train data shape, okay, so if I do dot format and x train dot shape, you can see that it has like 112 rows and 4 columns, right? And the 4 columns being sepal length, sepal width, petal length, and petal width. Okay, similarly we can look at similarly we can look at the others. I'll just copy paste this and change a few things here. So if I look at the test one, so it has 38 rows and 4 columns, the same columns here, this 4. And if I look at the y train dataset, so it has 112 rows, which is matching to this x train data, right? So it has 112 rows, so y train dataset also has 112 rows, so it is fine. And the last one being the x test, y test, so I need to change this entire thing, so it becomes y test, and y test dot shape, we have 38 rows. Okay, because it is one dimensional, we do not have any values after 38. Now that we have seen how the x train and y train and x test and y test data looks like, we are ready to build our first model. Okay, so there are many classification algorithms in scikit-learn that we could use. Here we will be using a K-nearest-neighbors classifier, which is easy to understand. Building this model only consists of storing the training set. To make a prediction for a new data point, the algorithm finds the point in the training set that is closest to the new point. Then it assigns the label of this training point to the new data point. Okay, the k in K-nearest neighbor signifies that instead of using only the closest neighbor to the new data point, we can consider any fixed number of k of neighbors in the training. For example, the closest 3 or the closest 5 neighbors. Then we can make a prediction using the majority class among these neighbors. We will go into more detail about this in the coming videos, but for now we'll be using just a single neighbor. All machine learning models in scikit-learn are implemented in their own classes, which are called as estimator classes. The K-nearest neighbors classification algorithm is implemented in the K-neighbors classifier class in the neighbors module. Before we can use the module, we need to instantiate the class into an object. This is when we will set any parameters of the model. The most important parameter of K-neighbors classifier is the number of neighbors, which we have already said that will set it to 1. Okay, so let us now try to import the KNeighbors classifier. So from sklearn dot neighbors import KNeighbors classifier, and then we'll try to instantiate the class. So we have KNeighbors classifier, and yeah, this should be good enough. And also, because we said that, we'll set the neighbors and neighbors, number of neighbors, to be equal to 0. I mean, sorry, 1, right? Okay, so to build a model on the training set, we call the fit method of the KNN object, which takes as arguments the numpy array xtrain containing the training data and the numpy array ytrain of the corresponding training labels. So let us now write our code. So knn dot fit, and we pass on our data, which is xtrain and ytrain, and then run it. We can now make predictions using this model on new data for which we might not know the correct labels. Imagine we found an iris in the wild with a sepal length of 5 cm, a sepal width of 2.9 cm, a petal length of 1 cm, and a petal width of 0.2 cm. So what species of iris would this be? We can put this data into a numpy array, again by calculating the shape, that is the number of samples, which is 1, multiplied by the number of features, which is 4. So let us now write our new array. So let us call it xnew underscore new equals to numpy dot array, and let's pass on the values. So it's 5 comma 2.9 comma 1 comma 0.2. okay, so let me space it out a little bit so it is easier to read. So this is what our new array is. So if I try to print this out, x new shape, okay, and the format, and if I try to look at the shape of this array, you can see that we have, because we have just where is it, yeah, we have one row and we have 4 feature columns, so therefore we are getting 1 by 1 comma 4. Now to make a prediction, we can call the predict method of the KNN object. Okay, so to do that, I'll first define a variable called prediction equals to KNN dot predict, and then I pass on my array. Okay, so now if I try to print it, prediction dot format, and I pass on the prediction, right? And if I try to print the species name, so it will be predicted target name dot format, and what I do is iris target underscore names, because that's where we have the names, and then prediction, that is the value. Okay, so now if I try to run this, I'll get a prediction value of 0, and because it is 0, this corresponds to Setosa, and we can see that the name that we have is Setosa. Okay, so basically the iris species with such parameters or attributes belongs to Setosa. That's what our model has predicted. So now to evaluate our model, if so how strong is our model, or to understand if it is any good, we can use our test set. okay, that we created earlier. This data was not used to build a model, but we do know what the correct species is for each iris in the test set. Therefore, we can make a prediction for each iris in the test data and compare it against its label, that is the known species. We can measure how well the model works by computing the accuracy, which is the fraction of flowers for which the right species was predicted. So now if I try to like write, uh, suppose we name a variable called yPredict and we write knn dot predict, okay, and now we pass on our test set. So now if I try to print out uh, test set predictions, okay, and I use slash and for new line, okay, and then dot format and y dot and pass on this variable which contains our test set. So we can see that our test set is predicting our model is predicting the values of the test set as 2 1 0 2 0 and all these values, okay. So 2 means basically what was the name again, I have a poor memory. So yeah, 2 is basically virginica, versicolor is 1 and setosa is 0. So it is virgin I think virginica was 2 again sorry, yeah, virginica is 2, then versicolor is 1 and 0 is setosa, okay. So these are the predictions made by our model for the test set. So now if we want to see our test code, as in how closely our model was able to predict to the already existing label data, we can use something called as knn dot score method, okay. So let us see how to do that. So I'll just print it out, print test at score, and I'll basically this piece of code is basically used to restrict the number to a 2 decimal place, and I'll write knn dot score, okay, and then pass our test set y underscore test. So as you can see that we have a test set score of 0.97. So for this model, the test set accuracy is about 0.97, which means we made the right prediction for 97% of the irises in the test set. Under some mathematical assumptions, this means that we can expect our model to be correct 97% of the time for new irises. For our hobby botanist application, this high level of accuracy means that our model can be trustworthy enough to use. So let's summarize what we learned in this. We started with a brief introduction to machine learning and its applications, then discussed the distinction between supervised and unsupervised learning, okay. Then we formulated the task of predicting which species of iris a particular flower belongs to by using physical measurements of the flower. We used a dataset of measurements that was annotated by an expert with the correct species to build our model, making this a supervised learning task. There were 3 possible species, setosa, versicolor and virginica, which made the task a 3-class classification problem. The iris dataset consists of 2 numpy arrays, one containing the data, which is referred to as X in scikit-learn, and one containing the correct or desired outputs, which is called Y. The array X is a 2-dimensional array of features with 1 row per data point and 1 column per feature. The array Y is a 1-dimensional array which here contains 1 class label, an integer ranging from 0 to 2 for each of the samples. We split our dataset into a training set to build our model and a test set to evaluate how well our model will generalize to new, previously unseen data. We choose the KNeighbors classification algorithm which makes predictions for a new data point by considering its closest neighbors in the training set. This is implemented in the KNeighbors classifier class, which contains the algorithm that builds the model as well as the algorithm that makes a prediction using the model. We instantiated the class setting parameters, then we build the model by calling the fit method, passing the training data xtrain and training outputs ytrain as parameters. We evaluated the model using the score method, which computes the accuracy of the model. We applied the score method to the test set data and the test set labels and found that the model is about 97% accurate, meaning it is correct 97% of the time on the test set, right? So I think this is it for this video. In the next video we will look at we'll go more in depth with what supervised learning is. Okay, so I hope you found this video helpful. If you like this video, please give it a like and do not forget to subscribe to my channel. And yeah, this is it, and I'll see you guys very soon with new videos. Thank you so much for sticking by.